Why do we need energy for computation? This is a follow-up on the first episode of today, where I spoke about Fred Hoyle and his sort of communication with intelligence. And I want to elaborate on this particular question that I had towards the end of the episode. Why do we need energy for computation? I think computation, the way I see computation is, I want to piggyback on Chiara Marletto here. What we really try to do when we talk about computation is just try counterfactuals. We try possibilities of zeros and ones, just to simplify. Of course, it's more complex. And what mathematics is and algorithms are just a simplification of that process. So instead of going always back to the first layer and trying all possible iterations, we use math, which in my view is just a higher level representation of the underlying relationships in the physical world. And then we still do fundamentally what we still do is we do iteration, and we try to eliminate bad solutions and surface the good solutions. And fundamentally, this is also what quantum computing is all about. So I want to talk about this in this particular episode and try to elaborate on the relationship between energy and computation and intelligence. This is Not Even Wrong podcast. It's September 17th, 2021. This is Krim Delco. This is the second episode, so nothing has changed. We are still up 14.4%, and the market's up 18.8% for the year. We're underperforming by 4.4%. What I mean is nothing has changed from the last update. So let's just jump right into it. The question, why do we need energy for computation? Why is intelligence another word for computation? So why do we need energy for intelligence? And in Fred Hoyle's book, the communication by the black cloud to humans is, you guys have the wrong physical representation. You can't use as much energy. That's why your computational abilities are limited. And that's why you are not going to be as intelligent as we are. Now, the solution for that is, of course, to take intelligence out of our brains. For that, we need to develop intelligence that is as good or not, if not better than our brains. And that's, I think, kind of what we're on the verge of doing right now. So there is hope for us that we can free ourselves from our bodies and actually have intelligence that is manifests itself in different ways. For example, in this particular book, Fred Hoyle's book, it's the gaseous form that is so promising, but it could be something else. Now let's talk about the fundamental question. What is computation? Computation is, to use Chiara Marletto's words, it's the exploration of counterfactuals. This is, in a nutshell, what computation is. We have counterfactuals, so we have potential zeros and ones. Let's keep it binary, very simple. So we have a switch, which can be 0 or 1, and a computation would be the exploration of this switch to see if it is 0 or 1. We could do, let's say, a small Python program for that. If 0, say yes. If else, no, or something like that. Underlying that would be a computation, which in computer language means something like a register would be either switched on or off, and then from there you would go back to the higher level program and show the result. So computation is the exploration of counterfactuals. Now, having said that, of course, that's not where it ends. The question was, why do we need energy for computation? Well, we need to do something with those counterfactuals. For example, let's say if you were in a valley in the Alps and you know that there was a rock fell down from the mountain, and it fell in one valley or the other. And that's sort of, because of that, you have the ability to maybe deduct what happened. What was there, an earthquake, or was there no? Because if it fell in this valley, for sure it can only happen as an earthquake, and if it fell in that valley, it wouldn't be an earthquake, with something else. So in that sense, you would have to walk into that valley and see if the rock is there. So you need to use energy to go and see which counterfactual actually is or isn't, and therefore you can also decide, okay, you did a computation. In this sense, the computation was simply going to the valley, but it's still a computation because it is well, maybe computation is a bit of a stretch at this point. Maybe it's better to talk about exploration, like I said, exploration of counterfactuals. So you could say that instead of using the word computation, you just use the word exploration of counterfactuals. If we use that, I think it makes more sense to talk about energy usage for exploration of counterfactuals. Because in order to explore counterfactuals, you need to do things. You need to actually do things. In my Swiss example, well, you need to walk to the valley. And in other examples, there's other things you need to do. And I think the point is that energy is, you can use energy for exploration of counterfactuals. Now, what we've been doing as a human race for at least since Galileo, but definitely before also since the Greeks, but Galileo introduced math to the sciences. What does that mean? What is math? Math is a higher level representation of counterfactuals, or it's a higher level representation of relationships in the physical world. The laws of physics are nothing but a very concise, compact way of saying what is, or at least conjecturing what is. So the laws of physics, if we say the Newton's law of motion, it's just a very short way of defining what is actually happening. And of course, to use Alexander's words in Fred Hoyle's book, The Russian, who says no science is worth anything if you can't make a prediction. So of course, that concise statement of what is only has value if you can make predictions. That's kind of course, that's not true in an epistemological way. We don't believe in that because we're not inductionists. But what I think is definitely true is that you cannot base, you cannot develop, let's say, a law of physics on something which makes predictions on things that already have happened or something along those lines. You can't predict the score after the game. There's no use for that, for sure. So let's get back. So the game of mathematics is to represent relationships, or what is out there, what is actually going on in the real world, in a more concise way, so we can use that to explore counterfactuals. So we use mathematics to develop algorithms to explore counterfactuals, which is nothing but trying to make a very tedious process of exploring counterfactuals a little bit easier. This is what it really is all about. So in a nutshell, the reason, or I still haven't answered the question of why energy, but let's assume we need energy for exploring counterfactuals. Let's go back to my Swiss Alps example. And now extrapolate that to the most complex kind of computation you could ever think of. And then think of, well, you could do that same computation a la Swiss Valley example. You could go here, you could go there, you could go here, you could go there, and so on and so forth. Or you could say, how about I find relationships that are shortcuts, relationships, mathematical propositions, those sort of things, that we can then use to evolve a theory of what is and what isn't. And in that context, that's where intelligence comes in. Now, what's the relationship between intelligence and computation? So why is intelligence dependent on computation? Well, like I said many times, and I think this is probably the fundamental approach of Orange Capital Partners, we're very Popperian in the way we see the world. And Popper would say that it's all about try and error, or in other words, it's conjecture and then falsification of the conjecture, or just show me what is and then show me if it's wrong, and if it's wrong, improve it. Error correction. How do you correct error? Well, you explore counterfactuals, and then you correct the errors that you find in those counterfactuals. So that's why that's what intelligence is. Intelligence is exploring of counterfactuals to the point where you can do error correction at a faster pace than you make errors. And therefore you start creating better views of the world, views that help you get certain things done. Because intelligence, in the end, it has to have some purpose. The intelligence, the black cloud, for example, the black cloud had a purpose, which was, okay, I don't know what the purpose of this black cloud was, but it had intelligence. And for example, it was able to learn the English language within, I think, a week. So whatever that intelligence was, it probably through self-learning, given the data that we sent them up in this particular book, the humans sent books and things like that to the intelligence. So the intelligence has the ability to learn English in a super fast way. There is a purpose to that type of intelligence. There is a purpose to, I guess that intelligence has figured out a way to explore counterfactuals in a very fast way, either through using enormous amounts of energy with very low-level math, or the other way around, or something in between. And that's really what the key is in terms of intelligence, no matter which kind of intelligence we talk about. So I think what Fred Hoyle's book really boils down to is the beauty of showing us what intelligence really is. Intelligence is the exploration of counterfactuals with a certain purpose, with a certain ability to do something. We don't know what the ultimate purpose is. Is it what? To create things out of atoms and eat them? But that can't be, we don't know. That's fine. That we don't know. But what we do know is that the faster we can explore counterfactuals in a specific domain, the faster we can understand what's going on and maybe extrapolate something useful for us. There is such a thing as being useful. Because we have purpose, we're driven. And even though we might be in a paperclip economy, even though maybe what we're doing might seem as a joke from outside, it doesn't matter. For us, in the game, it's not. Intelligence is useful. Energy helps us explore counterfactuals. Exploring counterfactuals is the key to intelligence. There's two ways to explore counterfactuals faster. One is to do it with more energy. The other is to do it with more math. The best is, of course, a world of both. Math does it more efficiently. Energy just does it in a raw way. The more energy we have, the more we can do. The more counterfactuals we can explore, the faster we can correct errors. And there is a rat race here between error correction and error making. And the more intelligent we are, the more errors we make. So there is a rat race here. And human progress and development depends on that relationship between the speed of error making and the speed of error correction. So in the Stone Age, the speed of error making was very small, and the error correction was even slower. And that's why it took a long time for us to evolve. And I would say my conjecture is that with the availability of either mathematical technology or energy or both, we have an incentive to make faster errors because we know intuitively that we can also correct them. So I don't know what the relationship is, and this is very Popperian here because I just came up with an idea that the speed of error correction and the speed of error making, there's a certain relationship with them, and there's probably a certain optimal relationship for progress. I don't know what that is, and this is for another podcast or maybe a grad student's PhD work, but the point here is that I think if we go back to the Stone Age, we just don't make any errors. We try not to make errors because we know we don't have the technology, the energy to error correct, because we don't have the ability to explore counterfactuals. The hunter in the Stone Age was always going to the same valley where all those animals were. He just didn't have the energy to go to all the other valleys and maybe find out that those same animals maybe are even easier to catch in other valleys. So again, energy usage is paramount in the exploration of counterfactuals. To finish this episode now, I want to go back to the relationship between counterfactuals and mathematics. And I want to talk about quantum computing in particular, because if if intelligence depends on the exploration of counterfactuals, then mathematical technology can help us explore counterfactuals faster. So for example, before I go to quantum computing, I think the last time we had a big breakthrough in mathematical technology was Newton and Leibniz when they came up with differential calculus. And what is differential calculus really? It's just telling us, listen, when we see something today, we are able to create a closed down formula maybe and also know how it's going to behave in the future. So isn't this helping us enormously deal with counterfactuals? Instead of having numerical solutions for every problem, we can just put a closed down formula, and that is so much easier. We can now start building machines and bridges, and the whole age of the Enlightenment was based on the development of differential calculus. Even though maybe in the limit it was wrong, it was not precise enough and whatnot, it helped us do all these phenomenal things. I think the next big breakthrough in mathematical technology, of course, is quantum computing. Now, what is quantum computing? Honestly, I don't know exactly what it is. It is based on quantum mechanics. Quantum mechanics, as we know, is the idea that the counterfactuals are manifold and that we sort of see one of them, either if you believe in the multiverse interpretation of quantum mechanics, then what it means is just that in this one universe where you live, this is one counterfactual, and there's many, many more counterfactuals out there. And quantum computing somehow is able to take advantage of all these counterfactuals and make faster conclusions, even in this particular universe where we are today. I'm not in the business here of explaining, of trying to interpret quantum mechanics, but what I'm trying to do here is just show, I think this shows very nicely that quantum computing as a tool for exploring counterfactuals can be very useful and therefore increase our ability to error correct through computation, and therefore also give us enormous amounts of ability to make faster errors. For example, we could create materials that can absorb the energy of the sun much, much faster because we can iterate much faster, make a lot of errors. We know we're going to make those errors, but we're still going to be able to succeed. I think the ability to do fast error correction also shows itself. For example, take SpaceX. Okay, Elon Musk is ready to blow up rockets at a faster clip because he has I guess he knows he has capital, but he has also a technology, a way to design these rockets, so he knows that he can also rapidly error correct, and therefore he can take that risk and build starships that go to Mars. And sorry for that digression, but I think that the more energy and the more mathematical technology we have at our disposal, the more we are actually, we have the ability to progress much faster. This is my point. I think this is the big takeaway from this particular episode. Thank you.